Okay, so this is a Bayesian test of hypothesis 2. Now let's go back to the law of total probability. So one was, so X is in fact has some distribution with some data. So it can be like, say, X is, say, binomial, and P, and the theta here is P, or something like that. So we have some cases here. Case number 1 is X discrete and the theta discrete. That's the one which we had before even starting this thing. So when we say X equals A, that is like saying that sigma is I from 1 to something, and say whatever P of X is A, given theta is, say, theta I, P of theta is theta I. So this was what we had before. We discussed that a lot. So that's case 1, discrete, discrete. Now we have case 2, which is discrete and continuous. So let me erase this, and because I have to write down here. So that is case 2, X is discrete and theta is continuous. In this situation, we find the D of P, X equals A, say. So that is P of X equals A, given this theta is between, say, some small theta and small theta plus d theta. This is just capital theta times P of this small theta less than big theta is small theta plus d theta. Now, this one is in fact interesting. Let's look at the situation and see what this thing is. First of all, when we say theta is continuous, so it means that this has some distribution. It has some distribution with PDF G theta. So if I look at that, so we have, say, G theta something, and this is theta, and we have the graph of G theta. So we are between theta and, well, let's just exaggerate, theta plus d theta. Now, what is the PDF? PDF is, in fact, density of the x-axis. So that's density of the x-axis when the x-axis has mass 1. So it has the name, probability density function. So that, in fact, is density of the x-axis. So, and the probability is in fact the mass. It is mass of this part of the x-axis from theta to theta plus d theta. So what is it? It is in fact density of this small portion times its length, which is d theta. Now from theta to theta plus d theta, this density doesn't change. So the change in density is small. So at this point we have g theta, and it's almost the same thing here. So then I can say that density of this small portion is small. So this mass of this, mass of the interval mass of this interval, theta, comma, theta plus d theta is in fact P of this. Okay, now let's go back to Calc 2. So mass of this thing is simply what? It's simply this function times this. So it is g theta, d theta. Incidentally, this g theta, d theta also is what? This area, which we always knew that probability is in fact area on the PDF graph of the PDF when it is continuous. I could have also said that in fact this probability is this area, so it is g theta, d theta. That's one way to say it. Another way is in fact this. And in fact, this is the reason that we say that. But anyways, so what do I have here? Let me erase this and write it in this format. So this this thing here is in fact g theta d theta. So we have a differential, and integrating this differential will give me t. So this equals p of x equals a, given theta equals theta. In fact, when d theta goes to 0, we simply have small theta here, g theta, d theta. So p of x equals a, that law of total probability becomes theta L, theta U, because it's on theta, p of x equals a, given theta, g theta, d theta. So that is the law of total probability when x is, so this is case 2, I forgot to write something. So that's case 2, x discrete and theta continuous, and theta has distribution with PDF g theta. So that is this case, and the case 3 is when both of them are continuous. So let me write it here. Case 3, this is continuous, and it has some distribution, theta, and theta also is continuous with some distribution. PDF g theta. But we assume that x comma theta has a joint distribution with joint PDF fx theta. So that's our assumption. So this g theta is the marginal distribution of that. Okay, so what in this situation we are trying to find what? We are trying to find this thing. We of say x is between whatever x and x plus dx, right? Because that's continuous, so it's not fixed at some point. So we have to find the differential of this thing. So let's just write d, and that is p of that x between x and x plus dx, given that the capital theta is between theta and theta plus d theta times p of this. Capital theta between theta and theta plus d theta. Okay, so let me okay, similar to the previous case, this is in fact the marginal g theta d theta. What is this? This one also results in this part results in that function fx dx. Okay, so we have both dx and d theta. So this will eventually be this one will be f of x comma theta, say dx, and also I have g theta d theta. See, this results in this, and I can draw some picture like that for this one, but let's not just do that. So that is in fact dp, and the integral of this thing will give me this property. So let me erase all these things and also d. So this will be integral. It is double integral depending on which one goes first. So it is from like x0 to x1, something like that. And f x. I need the second integral. So the second integral will be from theta theta u f x theta g theta, and the first is d theta dx. Okay. So, and well, this results in this another between x plus dx, so this will be p of x between x0 and x1. Okay, so that is the law of total probability when both are continuous. Now this helps us in doing Bayesian stats a lot. So let's do another problem, which is in fact the problem I started yesterday. In this time, it is just a continuous case. So what was that? Let me find it here. Oh yeah, this is in fact. Okay, we tossed a coin 20 times and we get 12 heads. Do you think the coin is fair? Okay, so we toss a coin 20 times and we get 12 heads. Is the coin fair? Okay, so I said you can say something like this. You can say, okay, fair means that non-hypothesis, that's none. And that is assuming that the p is in fact 1/2. Well, I should say that if x in fact is binomial, 20 comma p, and x is the number of heads. X is number of heads in 20 tosses, right? So that's binomial. So h0, and now in this situation, h1, to be fair, we just say, okay, yesterday I assumed that it was like 12 over 20 or something. But I just said it can be just any number between 0 and 1. So why not saying that it has a distribution? Uniform 0, 1, right? In a sense, it means that it can be any number between 0 and 1. So that is the alternate hypothesis. Now, remember, the first thing we do is, in fact, finding P of x equals that 12. So, this is P of x is 12, given that P is 1/2 times P, well, let me, in fact, this one is, let me write it larger so you don't get confused. So big P. P is 1/2. And remember, this, both of them happen equally likely. So both of them happen with probability 1/2. Okay, so this is 1/2. And plus P of x is 12, given that small p has uniform distribution. Zero, 1 times probability that small p has uniform distribution. Okay, so that is in fact P of x equals 12. So let's find these two. Well, let me write it down more carefully. So let me erase all these things and okay, so P of x equals 12 will be, the first part is, so I have binomial, so that is 20, 12 times 1/2 to power 12, 1 minus 1/2 to power 8, times 1/2. So this last 1/2 is this one. The second one is law of total probability, right? So this is in fact, it has a distribution. This is discrete, continuous. So that one is in fact integral. So integral is on p. So p goes from 0 to 1, right? And I have P of x equals 12, given small p. And what is the distribution? The PDF of uniform. PDF of uniform is this thing. This thing has PDF 1. So g theta is simply 1. In fact, it is not g theta, it is gp. This is not g theta. This is gp because I used p. Okay, so that is it. That's it. That is in fact, well, it's not really that is it. No, sorry. So let me erase this and write it down because this one is in fact not that simple. The other one is just a number, but this one is like this. So we have the first one is I found this. I found that to be well. I just calculated, but anyway. So that is 20, 12 times 1/2 to power 20. And this one is integral from 0 to 1. What is this? This is in fact 20, 12, that's just a number. And p to power 12 times 1 minus p to power 8 times 1 times dp. So I'm dealing with an integral like this. An integral like this. So if I bring this out, what remains is an integral like this 0, 1, p to the power 12, 1 minus p to the power 8 dp. And it goes from 0 to 1. Such an integral is like, it's called the beta function. But just use your calculator or Wolfram or something to find this. And if you use the calculator, you will see that this is almost I found it, and that was 0.4580. Okay, so don't try to do this, although it's like a beta function, it's gamma something times gamma something, and it's not that hard to find, but in fact it's like some factorials multiplied and divided. But anyway, that's not the point here. But I just want you to see how this law of total probability works here. This is in fact an integral when we have discrete continuous. And the g theta is this. Now I could have chosen something like a beta distribution. Beta distribution is good for these situations because its support is 0, 1. So so p is something between 0 and 1, and beta distribution is between 0 and 1. The PDF is defined as 0 and 1. It's 0. So that's one choice then. You can choose some kind of beta distribution. But anyway, so we have this thing. Now, what I want to find is, in fact, P of H0 given X is 12. So I have to find both of them. Probability that H0 or the null hypothesis is true given that I have observed 12 heads in 20 tosses, right? So this is, let's do it. I can write it the other way around, but let's do it. And so that is X is 12 given H0, probability of H0, divided by P of X is 12. Okay, now I know when I finish this thing, you might say, okay, there was no need for the X equals P of X equals 12 because that cancels out. Yes, when you are finding that K, the Bayes' say factor, you really don't need that. That's true. But it was just a good practice on how to find it. But anyway, so if I do this, this is in fact the first part. See, this is this part. So that is in fact this part here. That is P of X is 12, given that small p is 1/2 times P of small p is 1/2. Okay, divided by this, which is 0.4580. Now, if this is this part, which still is still here, so this will be, I calculated that, and that is 0.9480. 0.9480. Okay, so let's write it somewhere because I'm going to write the other one. So let's make some room here. P of H0 given X is 12 is 0.9480. Now I need the other one, P of H1 given X is 12. So H1 is H1, that's the same thing. So H1. Now what is this one? This thing here is in fact this. Oh yeah, I forgot to multiply this by 1/2, right? I didn't forget that when I was doing it anyway. Sorry, so I forgot. So this is in fact this whole thing. This thing times 1/2 divided by that, and this is almost say that is 0.052, 0.052. 520. Okay, so I'm ready to find that basis factor. So let me erase all of these things. It is in fact 80 given x is 12. I'll divide by. And I divided that as 18.20. Okay, now what is the conclusion? So what is the decision in fact? Well, there are different people are given different ideas about this. One of them, which I in fact have in my notes, that is I can't remember who gave this. So it is like this. It's like saying this K, and they call it strength of evidence. The strength of this. So they say that if K is less than 1, less than 10 to the power 0, which is in fact 1, then they call it a negative, so supports each one. So negative, this one supports each one. So if I have something between 10 to the power 0, so it is between 10 to the power 0 to 10 to the power 1/2, then they say that it is barely worth mentioning. So barely worth mentioning. Okay, so that's not really good. And they say if it is 10 to the power 1/2 to 10 to the power 1, so 10 to the power 1/2 is like 3 point something, right? So so it is between 3 point something and 10. Then substantial, so substantial supports H0 between 10 to the power 1 and 10 to the power 3/2. So 10 to the power 1/2 is almost 3, so that is like about 27, right? So strong, and that is strong, supports H0. And I guess there are two more between 10 to the power 3/2 and 100, 10 to the power 3/2 and 10 to the power 2. That is say very strong, and supports H0. And at last, if it is bigger than 1000, that gives me decisive, which means supports H0. Okay, so that's it. So that is now where is our that number? Our basis factor is 18.23, and that is here, right? It is in this zone. It is in this zone, and so we say that it is strong and supports H0. So we support H0, and we say we think that in fact that P is the probability of success is in fact 1/2. Not in fact, but the evidence supports that it is 1/2. Now, you might say, okay, that's not enough. We have to do it more than just 20 times. Yes, true. If you do it like 10 million times and you get like 5 million, then definitely supports that. So that was a nice and good example of how this thing works, and except maybe for the last part, which is some kind of decision making, and that decision making is based on idea. Okay, so it's your idea to accept that when it is bigger than this, you say, okay, I think it is enough. So it is decisive, or it is strong, or it is not strong, or it is negative, blah blah. So, but you can see that this, even by looking at this thing, you say that the probability that H0 happens, that was the null hypothesis, given the evidence, is 0.94. That's like 94%. The other one is 0.0. That's 5%. So really, that's huge. Now this one 10 to the power 10 squared is when like this. These are not. I mean. The other way around, when you add them, should be 1. This should be 1. So this can be like, let's say 0.5, and this can be 0.00001, say. Then you will get a huge number. Okay? So this, none of them should be too strong. But it is the fraction. I mean, when you divide them, that k. See, the factor should show you strong. Strongness or weakness of that. Well, anyway, so that is a nice example that it was also not just a test of hypothesis, but also on that law of total probability. When you have continuous, you have assumed a continuous distribution for the parameter. Okay, so let me stop this recording.